let's talk about the Caesar cipher. It was the first mathematical cipher used in human history. It was used back in ancient Rome by Caesar. He used it for his private communications with the different legions on the battlefield. So there was another cipher though at the time, and it was called Scytale, and it was used in ancient Greece by the Spartans. Essentially, it wasn't mathematical at all. What it would use is a stick and a belt with some numbers on it, or letters, and it would wrap around the stick and essentially line up perfectly to give you the encoded message. But today we're here to talk about mathematical ciphers. And these are going to be classical ciphers that will then transition into modern ciphers, which will then transition into quantum ciphers, or quantum encryption, or communication. So, in order to start this, we need to understand the difference between encoding and mathematical operations. The most simple and basic mathematical operation is going to be a modulo operator. And essentially what this does is it's like a clock, and you can only have certain numbers on that face of the clock. So for example, if you're looking at a traditional AM PM clock going from 0 to 12, then the modulo would be 12. But in this scenario, we're going to look at a modulo of 26, since there are 26 letters in the English alphabet. In order to get started, let's work with a few simple basic problems. The first three, so 4 modulo 2 is going to be 0 because 2 goes into 4 twice. However, for 12 modulo 7, there's only one time that 7 goes into 12 with a remainder of 5. So that would be the answer. When we're looking at the English language, and we're looking at specifically lowercase letters, which is going to be in the 97 to 122 range on the ASCII table, ASCII 2 table, you want to be able to derive a number that will then be encoded so that we can shift it mathematically 3 spaces. A simple example is going to be 27 modulo 26. That equals 1. And if we go over to the ASCII table, assuming we subtracted 97, then we'll be able to derive what the letter is associated with that modulo value. So in this case, 27 is actually just B, because we're using the modulo operator to then derive 1. So if we were to take a message, or in this case, clear text, we would be able to encrypt it and decrypt it based on the Caesar cipher. So in this example, we're going to use SIGINT. And before the video started, I encoded SIGINT with the particular ASCII 2 values subtracted 97, since the lowercase a starts at 97. In this example, SIGINT will then translate into 18, 8, 6, 8, 13, and 19. And so how the Caesar cipher works is you add 3 to each value. And in this case, we're given different numbers that are associated with the same message, but shifted 3 spaces. And in this case, we can look up the values in our ASCII 2 table over here. In this case, we're going to have V, we're going to have L, J, L, Q, and W. So our final answer will be this, and this is the encoded value. In order to get the decoded value, or in order to decrypt it, the process would be reversed. So instead of adding 3 spaces, we would just subtract 3 spaces from it. So 21 would become 18, 11, 8, 9, 6, etc. And we'd be able to do this across the whole message. Now, the Caesar cipher is very specific for something called the Affine cipher, which we'll cover later. But the Caesar cipher only deals with shifting 3 spaces at a time, when the Affine cipher is able to shift and use a modulo value associated with the key. But we'll cover that later. I hope you guys enjoyed the video. I look forward to making more and seeing you guys on the channel. For individuals interested in cryptanalysis, you can go on my SIG Crypto site and look at that information.